Hello and welcome to this presentation on superreconciliation with horizontal gene transfers. Superreconciliation is a framework that's concerned with the study of the evolution of synthenies. And by syntheny we mean two or more genomic regions that may contain one or more genes and are derived from the same ancestral region through evolution. To give some examples of such synthenic regions, we can take operons in bacteria or the homeobox gene clusters. Now it is very important to take into account such evolutionary relationships when trying to build phylogenies of the gene families inside synthenies, especially when we are using parsimony frameworks. Indeed, with synthenies, a single event can affect several genes at once, and if we study the evolution of each gene family individually, the same event can be counted several times. There are several methods that have been developed to address this problem. For example, the DILTAG method, the DCOSTOR method, or methods that are based on duplication episodes. But the one we're interested in here is the superreconciliation method. First, let's go through a few basic definitions on superreconciliation. Here you can see a graphical representation of a superreconciliation. There are a few things to notice in that picture. First, it is made up of two trees, a syntheny tree embedded inside a species tree. To that respect, it is quite similar to a classical reconciliation. The inner tree is built on a set of leaves that represent extant synthenies of the family we're interested in. And the species tree contains the species that hosts those synthenies. This tree embedding displays a detailed history of the evolution of the syntheny family. If we start at the root of the tree, we can see that there is a speciation event here that led to the formation of two different copies of the syntheny in two different species. On the left branch, there is a segmental duplication that led to an additional copy of the syntheny in the same genome, but only of a segment of the original syntheny. On the right branch, after a partial loss that led to the loss of the genes A and B, we see that there is a transfer of the syntheny to the other genome through a horizontal gene transfer event. In general, the superreconciliation problem is to infer such a detailed superreconciliation starting from the knowledge of the syntheny and the species tree. And because this is a parsimony approach, we are seeking a superreconciliation with the minimal number of evolutionary events. Now there are two main versions of the problem that we will consider here. The first version is the ordered superreconciliation problem. In this version, the synthenies are sequences, and the relative order of gene families must be conserved throughout evolution. In the unordered version on the right, synthenies are modeled as sets, and any number of rearrangements are allowed. Our group has been studying this problem for a few years. We mainly focused on a restricted version of the problem called the DL version. In DL, the set of allowed events is limited to segmental duplications, segmental losses, and full losses. In the DL setting, the ordered version is NP-complete, although it is fixed parameter tractable with respect to the number of gene families that we denote by T. The unordered version, on the other hand, is polynomial, and we know of an O of Tn algorithm, where n is the number of nodes in the syntheny tree. The fact that the unordered version is polynomial is actually one of the main motivations for introducing this version. Now, although DL is interesting as a theoretical starting point, you can see that it is quite limited if we want to apply it to real-world scenarios. Specifically, there are several important evolutionary mechanisms that are missing here. The most important one being horizontal gene transfers. This mechanism is at the heart of the evolution of bacteria. Another important mechanism that is missing is tandem gene duplications. This mechanism is at the root of the formation of synthenies themselves. So in this talk, the main point I want to address is how we can integrate horizontal gene transfers inside the superreconciliation framework. Horizontal gene transfers are transfers of genetic material from a donor species to a recipient species. From the point of view of our model, it is quite similar to segmental duplications, because it results in a new copy of the synteny. Although it is a bit different because this new copy goes in a new genome and doesn't stay in the same branch of the tree. This property means that the coincidence of the synteny tree and the species tree is broken, as you may see in this picture. The transfer events may actually jump from one branch of the species tree to another. Now the main question is, how can we infer super-reconciliations that allow for transfers and minimize the number of events? To see how we may do this, it helps to take a combinatorial perspective. Remember that the input of our problem is made up of two trees, a synteny tree that is shown here on the left, and a species tree that is shown here on the right. Each leaf of the synteny tree belongs to a species of the species tree. We may see a super-reconciliation as a combination of two objects, the first one being a mapping of the synteny tree onto the species tree. This mapping implicitly labels each of the internal synthenies as either a speciation, a duplication, or HGT. For example, the node here is a speciation event because its two children are located in two species, of which this node is the last common ancestor. The left node is a duplication because its two children are in the same species. On the branch from the root node to the left node, there is a full loss event because this copy of the synteny is only seen in the X species and is missing from the Y species. The second element of a super-reconciliation is a labeling of the synteny tree with ancestral synthenies. This labeling directly implies segmental losses on some edges, such as this one. This node is a speciation event and its left child is missing the C gene, so this means that the C gene was lost in a segmental loss event. What this demonstrates is that by choosing an appropriate mapping and labeling of the synteny tree, we actually decide of everything that composes a super-reconciliation. Now it is only a matter of choosing those mappings appropriately. Let's go through each of them individually. First, the synteny to species tree mapping. In the DL setting, the only optimal solution is to take the LCA mapping. The LCA mapping is simply a mapping that associates to each node the last common ancestor, or LCA, of the subtree below that node. This mapping contains 3 evolutionary events, so its cost is 3. If we allow horizontal gene transfers, however, the LCA mapping is no longer optimal, because, for example, we may move the mapping of this node to the species Y. This turns the speciation node into a transfer node from Y to X. By doing that, we save the full loss that I mentioned earlier. And overall, the number of events is 2. So if we are to look for the optimal mapping while allowing for transfers, we have to do a more thorough search of possible mappings than with the DL setting. This is actually what's done by the Bensel, Holm, and Kelly's algorithm that proceeds by dynamic programming. It constructs a table called C on 2 variables, V and sigma, and each entry of this table is the minimum cost of a mapping of the synteny subtree below V, assuming that V is mapped to the species sigma. It is possible to construct this table in big O of n times m operations, where n and m are the number of nodes in each of the trees. Now we turn our attention to the second part of the super-reconciliation, that is the ancestral synteny labeling. We are to label each of the internal nodes with a putative ancestral synteny, and we must do that such that the number of lost segments is minimized. It is important to note that in our model, any lost gene family cannot be recovered later in the evolution process. In the ordered setting, we have no choice but to try all subsequences of all valid orderings of the gene families. This leads to a number of options in the order of 2 to the t times log t plus t. In the unordered setting, on the other hand, we only have 2 options, and this is because there may be at most 1 loss on each edge of the synteny tree. So the first option is to choose the minimal set of all gene families that are in the subtree of the node. This choice would incur either 0, 1, or 2 losses below the node. We may also choose any larger set than this one, and this would incur exactly 2 losses, 1 on each edge. Now we know how to calculate each part of the superreconciliation. If we were in the DL setting, it would be easy to go from there to the final algorithm, because there is a nice result that says that each of those parts can be minimized individually and still result in a global optimum. However, in the DTL setting, this is no longer true. Here you may see an example of why. Both of those superreconciliations are from the same input. On the left, the first mapping led to only one duplication, whereas on the right there are 2 transfers. So if we were to minimize the first component of the superreconciliation, we would say that the first is the optimal one. However, if we use the first event labeling, we will be forced to have 4 segmental losses, whereas on the right case, we can do with only 2 segmental losses. So overall, the number of events on the left solution is higher than on the right solution, even though the mapping we started with was more costly. So in the DTL setting, we must optimize both parts at the same time. This can be done by adapting the dynamic programming formulation from before. We will create a table that ranges over 3 variables. The first 2 are the same as before. The new variable is chi, which is one of the possible syntenies. If we assume that we have already computed this table, it's quite easy to extract the overall solution. It would just be the minimum value of the table, provided that we fix v as the root of the tree. Now the complexity of computing this table differs whether we are considering the ordered version or the unordered version. In the ordered version, we get a global complexity of n times m squared times t times 2 to the t log t plus 2t. In the unordered version, it is a bit simpler because we don't have to consider so many options for the synteny, giving an overall complexity of nm squared times t. If we compare the complexity of the DTL algorithms that we just described with the DL complexity, we see that they are quite similar. We just added a new term that is m squared. So although DTL is likely to be NP-complete in the ordered version, just like DL, it is still fixed parameter tractable with respect to the number of gene families. In the unordered case, it is still a polynomial algorithm, although a bit slower because we have to range over all possible species. Now that we've looked at integrating horizontal gene transfers inside superreconciliations, we turn our attention to an ongoing work on tandem duplications. Tandem duplications are local duplications that create new copies of the genes inside the same syntenies. If we have a synteny ABC, we may have a tandem duplication of the segment BC and get a new synteny AB squared C squared. Here we will focus on the easier version of the problem, that is the unordered version. The first step we need to take is to allow multiple gene copies in the same synteny. This can simply be done by using multisets instead of simple sets. Now, between any 2 synthenies, there is a new type of event that may happen, that is tandem duplications. Such events amplify the existing gene content in the synthenies. It may not create new genes, so this second example is not valid. Contrary to partial losses in the unordered version, there may be successive tandem duplications on the same branch of the tree. If we go from 2 copies of the A gene here to 5 copies, there was at least 2 tandem duplications to get there. This complicates the model because we no longer have only 2 choices for the synteny. Let's take a look at this example. Here we have a tree that is already labeled with events, and we just need to find an optimal synteny assignment. What we can do is take the intersection of each synteny. So for example, on the left, we get AB to the 4th C, and this C is here because we need it in the left child. On the right, the intersection gives ABC cubed. and the root will only be ABC. This assignment has a cost of 11 events. We can do better by factoring in the tandem duplications related to gene B. If we move them all to the root, like so, we save one tandem duplication. This shows that there are multiple solutions to consider at each node. Our current conjecture is that we need to choose between taking the intersection, the union, or a larger set of genes. So to sum up, the key point of this talk is that superreconciliation actually lends itself pretty well to handling horizontal gene transfers. The only catch is that because we need to be more thorough in our search, we have an added factor of m squared in our optimization algorithms. We have started considering extending the method to tandem duplications. We are also considering extending the methods to gene gain events. In the oncoming month, we will focus mainly in validating our model via simulations and then to applying it to study the evolution of syntenase. Thank you for your attention, and please let me know if you have any question either in the Q&A window that is coming or in the discussion period afterwards.